Today's lesson is about sampling distribution models. So the first thing I want to introduce is what we call the central limit theorem. And the central limit theorem, which we also abbreviate as CLT, it's a very important idea. When you first see it, it's super confusing, so just know that we'll go over some examples that have pictures in class. But for now, keep it at the back of your mind. The basic idea behind it is that if you take many large samples for the same thing, then from all of your samples, the means of these samples are going to follow a normal model. And this was discovered by a French mathematician named Laplace. He did many, many important things. This is just one of them. So I'm going to go on to some important notation. And you've seen a lot of this stuff before, but I just want to make sure you have it again. I think it's not going to hurt you to have it all in one place. So the population mean, you have often seen represented as the Greek letter mu, whereas the sample mean is usually represented as x bar. Or sometimes, I think in your book, it uses y bar. So the population standard deviation is the Greek letter sigma. This is a small sigma, the big one you've seen for sums. So you'll notice that oftentimes populations do use Greek letters. There's a few exceptions, and actually you'll see one in just a minute. But usually if you see a Greek letter, note that it usually will refer to a population. The sample standard deviation you have seen used as S. So now the population proportion and the sample proportion are newer things. The population proportion, we just use the letter P, and yes, it's one of the many times you see the letter P. By the way, this is a lowercase p. And the sample proportion, we will use a P with a hat over it. We call it the P hat. So I think you've seen something with a hat over it before when you were doing regression. We had y hat, that was our predicted y, in this case, it's going to represent our observed proportion. It's going to be the proportion we see in the sample. And we have two formulas that we're going to use in the examples that we have for this chapter. So the standard deviation for the proportion of successes is going to be equal to the square root of PQ over N. So just a few things I'm going to write off on the side. P, remember, is our proportion. And oftentimes we'll call this our proportion of success. And if it has a hat over it, it would be our sample proportion of success. The Q is going to be our going to be our proportion of failure, or we can just say 1 minus P if you want to. The N is going to be our sample size. So that's our first formula. We're going to use it in our first 3 examples that we have here. Now the second formula is really confusing for many people. We will do a lot of examples with it, and it's going to come up again in many chapters, and actually the first formula will come up again in all the chapters that we're doing in the future. But the standard deviation of a sample mean is going to be sigma, which is our population standard deviation, over the square root of n. Now I will explain what that actually means later on in the video, but for now, this is a good introduction to this chapter. So let's do an example. This one is saying that of all the cars on the interstate, 80% exceed the speed limit. We're going to use the 68, 95, 99.7 rule to draw and label the distribution of the proportion of cars the police will observe among the first 50 drivers. So this rule right here is actually, you've seen it before. It's what you're going to use when you use a normal model. Just a side note, this actually sometimes is also called the empirical rule. You do not need to have it memorized. However, if you take a college stats class, they might use that term, so you'll know that that's the same thing. You tend to hear the empirical rule used a little bit more, but I think the one with the numbers that we have above is easier to understand because it helps you remember what the numbers actually are. So whenever you have problems like this, in fact, this is going to occur for pretty much the next 7 or 8 chapters of the book, which is the rest of the book. So just know that our first step is always going to be to check our conditions or assumptions. It starts, when you first do it, it seems like it takes a long time, but it'll kind of become automatic once you do it a few times. So our first assumption is the independence assumption. So we are going to assume that all of the cars are independent of each other. What I mean by that is that, for example, a car is not following the car in front of it, which is also exceeding the speed limit. So we're going to assume the cars have nothing to do with each other. And in this case, you can make that assumption, but in other cases, you won't be able to. So this one is often going to be overruled by the next 2 assumptions, which are our randomization condition and our 10% condition. So the randomization condition would be if this was a random sample. So if the police officers who were checking these drivers picked a completely random sample, which maybe they did, I'm not sure how they would do it. It seems like it'd be very difficult to, but if they did, you would be able to say that this was a random sample. So now, in this case, they don't actually specifically say that, so I'm going to just put a question mark there. But know that the independence assumption is strong enough to overrule this one. So usually, they will say specifically they randomly choose 50 cars. The other thing that's important is what we call the 10% condition. So the 10% condition is where you look at the sample size, which in this case is 50. Make sure that it is not a huge part of the population. So what I mean by that is I would say that 50 is less than 10% of all drivers. Now we know that's true. 50 is 10% of 500. We know that there's more than 500 people driving on this interstate, we're going to assume. Unless it's really in the middle of nowhere, which I doubt. Most of the time, the interstates have many, many, many people driving on them. So 50 is going to be less than that. The last important condition that we have to check is our success-failure condition. So now in a problem like this, you could get by with checking just numbers 1 and 4. Or you can check 2, 3, and 4. But you have to check this one. And success-failure is, we sometimes call it NP and Q. The other thing we call it is we want to make sure it's a large enough sample. So I'm going to write that off on the side. And what we're going to be looking at is we are going to be trying to find our expected number of successes and our expected number of failures. So in this case, our expected number of successes would be our number of drivers that we're checking, which is 50, times the proportion of successes, which is 80%. So we are going to expect that we will get 50 times 80% of the drivers, which is 40, to be speeding. So that one is going to be our expected number of successes. Our expected number of failures is going to be 50 times the probability of getting a person who does not exceed the speed limit, which is 0.2. We get this by doing 1 minus 0.8. Remember that Q equals 1 minus P, so we get that. And we end up getting that that's 10. So that's our expected number of failures. Now, what we want to look for is we want to make sure that the expected number of successes and the expected number of failures are both at least 10. Actually, we just barely made it on this one. So 50 is probably going to be the minimum size our sample has to be. So both of these are greater than 10. I always like to put a little check to show that it holds, but you don't have to do that. And I usually write something like it's greater than or equal to 10, just to show that it's either what I want or bigger than that, because that's what we're looking for. We're trying to get these bigger than 10 or equal to 10. So our second step, and this is actually our last step, we only have 2 on these ones. Second step is to actually work the problem out using the normal model. So our mean in this case is our population proportion, which we knew from the previous slide is 0.8. That's our probability of success. Our standard deviation, we actually are going to use the formula that we had earlier, the PQ over N. So you'll often see this written as SD of P hat. It's kind of a weird notation. So this is going to be the standard deviation of the successes that we get from this sample. So it's going to be the standard deviation of the proportions of successes, I should say. And we can find that. I'm actually going to just write out, just in case, just to make sure we know what all of these are on this side. We do our P, which is 0.8. Q is going to be 0.2. N is our sample size, which is 50. From there, we get that our standard deviation is 0.057. By the way, make sure as you are working these problems out that you do show all of your work. If you just put mean is 0.8 and standard deviation is 0.057, you won't get full credit. So it's really important that you show which formula you used and what numbers you put in for each thing in the formula. So we have our mean, we have our standard deviation. Now we're going to use our normal model. And we have to draw it out, unfortunately. The other thing is, do not forget to give it a title. If you want, you can title it immediately, just so you know. I'm going to call this the proportion of speeders in 50 cars. It's good to be as specific as possible. So I know that my proportion, most likely, if I were to take many samples like this, I would generally always I would overall get a mean around 80%. And the other thing I know is that my standard deviation is 0.057. So the middle 68% is going to be between 0.743 and 0.857. I get these by both adding and subtracting the 0.057 from the 0.8. You're going to do the same thing, adding 0.57 to each thing, or 0.057, excuse me. And that will give you the rest of your normal model. So it's kind of long to draw the normal model out. If you want, you can write out in sentences. We expect that 68% of the time the police will find between 74.3% and 85.7% of people speeding, and 95% of the time we will find 68.6% and between 68.6% and 91.4% speeding. You can write that whole thing out, do the same thing for 99.7. It's long if you write the whole thing, but sometimes you are going to have to kind of to show exactly what your thoughts are. If you're taking the AP test, I recommend that you do write that out in addition to showing the picture. But in general, you'll also get other questions to answer about these, so just keep that in mind. So this is more typical of the type of example you're going to get with this stuff than the previous slide. And this actually should be example number 2, not 3. So they tell us that blue M&Ms are supposed to make up 30% of the candy sold. In a large bag of 250 M&Ms, what is the probability of getting at least 25% blue M&Ms? So this type of problem it's confusing the first time you see it, but it's still confusing even if you've seen this type of thing a lot. So just be careful when you see multiple proportions that you don't just dive right into the problem without thinking it through first. So the first thing I always like to do is define my variables, figure out what I know. So I know my population proportion, which is going to be my P without a hat. That's going to be the proportion of blue M&Ms for all the M&Ms in the world. And that's going to be 0.3. That is my population proportion. So then this 25% here is going to actually represent my sample proportion. I want 25% or more. So I'm going to use P hat for that one. And don't let the at least confuse you in the beginning. We're actually not going to really use the P hat in any sort of calculations yet, but we will get to that in just a few minutes. So the other thing I know is that my Q is my 1 minus P, which is going to be 0.7. My N in this case is going to be 250. So it's important that you know which of these numbers you need to use for your actual formula with the standard deviation. I'm actually going to calculate the standard deviation now since I have all this stuff written out. So my standard deviation is the square root of PQ over N. Notice how none of these values have a hat in them. Actually, sometimes you'll even see this written as standard deviation of the P hat of the sample proportion. That does make it look a little bit more confusing. For now, if you just want to write standard deviation, that is totally fine if you just want to write SD for now. So then I am going to use the 0.3 and the 0.7. Just make sure that you're using the 0.3, the population proportion, and not the sample proportion. It's very important, otherwise you're going to get the whole thing slightly off. So when we work this out, we get that our standard deviation is 0.029. So I need to, before I do anything with a normal model, I do need to check my conditions and assumptions. And I'm going to start with my success-failure condition. Which is my NP-NQ. And once again, I am using the p of 0.3, not the 0.25. So my n, my sample size is 250. My population proportion is 0.3. And I'm going to do a similar thing with the failure, which is the n times q. So my expected number of successes is 75. My expected number of failures is 175. By the way, just a side note, these numbers should add up to your 250, which is your sample size. And both of these are greater than 10, which is good. You can put a smiley face, you can put a check, I don't care what you do, but you're good now. So we're happy about that. The next thing that we need to do is a little bit more complicated. So usually you would check your independence assumption. In this case, it's a little bit less reasonable. The problem is with M&Ms, if you get them out of the same bag, we're going to assume that they are not necessarily independent. At least that's what we would think. However, you can assume that M&Ms are independent. It might, however, be better to use your other two. So the alternative to the independence would be the 10% condition and the randomization condition. So the 10% condition is actually pretty easy as long as you remember to do it. We would just say that 250 is less than 10% of all M&Ms. And this would be of all M&Ms in the world, which is definitely true. There's a lot of M&Ms out there. Randomization is a little harder because we don't know that this is a random sample of M&Ms. So what you actually can say that would be even better than randomization is that you can assume that your bag, that these M&Ms are representative of all M&Ms. So that's another way around the randomization thing. If you don't know if you used a random sample, this is another good thing to say. So it took a lot of leading up to this point, but now we are actually going to solve the problem. We want to find the probability of getting at least 25% of the M&Ms being blue. So we can use a normal model for this problem. And in this case, it didn't tell me to draw and label a normal model, which is nice. So I'm going to draw a normal model, but I'm going to make it a sketch. When you sketch a normal model, what you're going to do is you're going to put your mean in the middle. So we know that if we took many samples of M&Ms, approximately 30% of them would be blue, so that would be our mean. And we want to know the probability that we get at least 25% of them. So 25% goes below 30%. It's going to be down here. We are going to show this on our normal model by shading in above it. So this is our M&M normal model. Now what you can do is you can use your calculator in order to calculate this out. So in our calculator, we're going to do the normal CDF function. And our lower bound is going to be 25. Upper bound, you can do any really high number. In fact, you can even do like anything greater than 1, and that would be fine. I like doing something like 999, but any high number that you like is fine. If you want, also, you can always put like infinity or something like that. And then we're going to put our mean. And then we're going to put the standard deviation that we found in the beginning of this problem. I don't really care where you make the standard, where you find the standard deviation, as long as you do it somewhere. Sometimes it's also nice to put something like that you're using a normal model with a mean of 0.3 and a standard deviation of 0.029. This is our shorthand way of writing it. So if you want to put that, you can. So when we find this, we end up getting 0.9577 approximately. So what you would say is something like there is a 95.77% chance that we'll get at least 25% blue M&Ms. So our last example is probably among one of the more challenging things that we do in this class. By the way, this is example number 3. So it tells us that SAT scores have a mean of 500 and a standard deviation of 100. What do we expect the mean to be for a random sample of 20 students? So the first thing that a lot of people try to do is they like to say, okay, my mean is 500. My standard deviation is 100, and I'm going to use a normal model where I have 500 and then 600, and using a standard deviation of 100. Unfortunately, that is not right. Plus, it's super messy. So this is extremely wrong. Now, if you were to do that, this would be great. This would be right if there was only one student that you were looking at. Unfortunately, we are looking at a sample of 20. So what's going to happen, since our sample is bigger, we are actually going to have values that get even closer to our mean of 500. So what's going to happen is our standard deviation is actually going to decrease, because most of our values are going to be closer to our real mean. This is kind of part of the central limit theorem. So what we're going to do is we're going to use our formula, which is the population standard deviation. That's the one I gave you up there. So this was my sigma right here. And it's going to be that over the square root of n. By the way, you will often see this written as SD of x bar. If that is super duper confusing to you, don't worry about that right now. I don't want you to get the notation to mess you up. I just want you to kind of know which ones are populations and which ones are samples. That's the main thing I want you to get with notation. But just know that we're doing sigma over the square root of n. So in this case, our mean of our sample and our mean of our population are actually going to be equal. We're going to expect that our sample is going to approximately have a mean of 500. Our standard deviation of our sample, however, is going to be different. So we are going to do 100 over the square root of 20. This is going to give us a standard deviation of 22.36. So, as with everything in this chapter and pretty much every other chapter in the entire book, your next step is going to be to check your conditions and assumptions. So for these, there's really only 3 things I want you to check. In fact, you can get by with 2 of them, but I'm going to ask you to do 3. So the first thing is our randomization condition, and you're lucky because it even says right up in our problem that this is a random sample, so you can just write that out. This is a random sample. The next thing that we know is that 20 is going to be less than 10% of all students who took the SAT. The last one we're going to do is we're going to assume that these students are independent. Now, we can't be sure of this. For example, if whoever took this sample went to like Caltech or something like that and sampled everybody there, then they probably aren't going to be independent if they're all from the same place. However, we're just going to make the assumption that they are. So the last thing that you need to do for this problem is to make your normal model. And my normal model is going to have a mean of 500, and it's going to have the standard deviation that I used before. By the way, I recommend maybe write this stuff out somewhere just so it's clear what you're actually using. If you don't like this notation with the n, you can write normal model with a mean of 500, standard deviation of 22.36. That's fine also. So we're going to go ahead and write it out using this. We get these by adding our new standard deviation to the 500 and subtracting it. There's a few ways you can do this without having to write this whole thing out and draw the whole thing out, which mainly is writing it all by hand, writing out sentences. But I think this is really the easiest way to do it. It's a very nice visual way. And we can write this as, make sure you label it. This would be the mean of SAT score of 20 student samples. Or better to say something like samples of size 20 would be easier to understand. And you might want to label this out. If you want, I do still recommend that you do write out a sentence or two about what's going on here. So I would say something like, we expect 68% of samples with 20 students to have means between 477.6 and 522.36, and then do the same thing for 95% and 99.7. I know it's kind of long, but it's good practice just to see what's happening there. If you do write this out in words like that, you don't need to draw the normal model so specifically, but I think summarizing it in a paragraph is probably a good idea.